Okay, let's get started. So I put your graded quiz ones over here. Feel free as I'm talking to get them if you haven't already. So in general, the scores were a lot lower than I expected. And pretty much all of the questions were derived directly from the slides or just barely a tweak from something in the slides. So what I did is I made the quiz out of 10 instead of out of 15. So you can see the score on Blackboard, what you got out of 10 instead of 15. Those of you who have over 10, you keep the bonus points you got. And on the main page of the course website, I have the sorted list of all the scores that everyone got, just to see how did you fare with the rest of the class. And even if you did well, look at the ones that you missed and see, where am I not quite understanding something? Do I need to re-look at something in the slides? Do I need to practice some more coding examples? Do I need to re-watch the lecture videos? So this is just kind of a warning in some sense, because the test will be somewhat akin to what the quiz was like. Just instead of however many minutes it was, it'll be 50 minutes instead. So just be careful if you answered something that you thought was right and it wasn't. Try to understand why you missed the question instead of just thinking, oh, this quiz was worth nothing. Okay? Any questions about the quiz itself? Next quiz will be? Yeah, yeah, that's another thing. I'm making all the quizzes from now on take home because it was not easy reading your names. I'm not joking about that. But so what I'm going to do, because I can't enforce having people sit in a certain place during all of the lectures, because that would be micromanaging, what I'm going to do is I'm going to make all the quizzes take home instead. And then I'm going to have your name pre-printed on the quiz, and then you'll get them at the end of one of the lectures, and then you'll return it at the start of the next lecture. Okay? So, and it won't take any lecture time, and we won't have to worry about any of that sort of thing. Any other questions about the quiz? How are labs going for those who've been? Good. Okay. I've heard that from the TAs that C-Line is not installed on the computers. They're recommending some other websites. I made an announcement about one of them that you can use, so you don't need to install anything. You can just upload the source code there and then just run it from there. The only issue with that is that we're going to be working with multiple files at some point, and that source that I gave only allows for one file. So you may have to switch at some point. But for the interim, it's perfectly okay to use that one. One thing that I've been getting a lot of emails about is things related to programming assignment 1. So, and things that about that assignment that I've already addressed on the announcements page. So if you're going to ask me a question over email or in class or something like that, look on the announcements page first to see if I've already addressed it, because quite a few people have emailed me about the minor and major axes being flipped, and so that was entirely my error. The two are flipped, and so there's an announcement about you can have them in either order, because the definition I gave on the assignment was not actually correct. So just please check the announcements page. Any questions about the assignment? When's it due? Friday. So another thing was that Blackboard set a completely different date. I've updated the date to match Friday. All the other assignments are matching those, so that we won't have any other problems. But any questions about the assignment or anything else? Yeah. So I have every assignment have unlimited submissions. but the one that's graded is the last submission that you give. Yep, so you can submit as many times as you like before the deadline, which is Friday, for every assignment. Other questions? Yeah.
Are we allowed to take our own computers to the lab?
Yeah, you can take your own computer. Anyone using a tablet? One person. One person for each of the questions I asked, yeah. So you can take whatever you like, but there will be lab computers there if you forget your laptop or just don't have one. Yeah, so there's always a computer available for you. Other questions? Okay, so let's get back into the lecture material. So the last thing that we ended on, the last thing we ended on was this integer thing. So remember we had int, which stands for integer, and then there are different sizes of integers that we can have depending on how much data we'll need, or how many different numbers we need to address. So one of the questions on the next assignment that I will post probably tomorrow is, I've analyzed this program, and for this particular program, I figured out what are the range of integers this program is expecting to run. And then what you'll need to figure out is, what is the smallest data type of these that I could use? Do I need a long int, or can I get away with a short int? So being able to think, well, how much data do I really need to solve this problem is actually pretty important here. So remember, integers hold whole numbers. They can be either signed or unsigned. So what's the advantage of unsigned over signed? Why would I ever want an unsigned integer? Yeah. It's actually the same amount of memory for the same type. So if I use an unsigned int versus just a normal int, they take the same amount of memory. Yeah. What's that? You don't know what the user is going to input, but how does that help me with why would I ever use unsigned over signed? Store positive numbers, but? Yes, right. So signed, if you have, so think of a signed integer. I mentioned last time that one of the bits is called the sign bit, and there's a slide about this, I think. And all of the other bits in the number are used to actually represent the number. So 0 for the sign bit is if the number is positive, and 1 indicates that it is negative. So if I have an unsigned integer, that sign bit can actually be used to represent the number. I don't need a sign bit anymore. So in fact, I get twice the range that the signed number had. So if a signed number, for example, goes from -32 to +32, then a unsigned version of the same number would go from 0, because it can't go negative numbers, 0 to 64. Because I still have the same range, but I can go twice as far into the positive numbers as the signed integer did. So that's the advantage of having an unsigned integer. But another reason why you would want this is you want to communicate to the person that's looking at your code to say, oh, I never need a negative number for this part of the code right here, because it says unsigned. And so it's just a way of thinking, do I really need negative numbers here, or can I get away with positive ones? And so about the sizes here, I said that int can be 4 or 8 bytes depending on the computer that you're using. So either 32 or 64 bits, it depends on what you're using. I said that short int was half of the size of int, which is true. Long int, which is twice the size of int, which is also true. And I incorrectly said last time that long int is twice what long int was. So I should specify that long int is only guaranteed to be at least 64 bits. It's not guaranteed to be twice as many as long is. So you can only guarantee that it's at least as large as the long here. So pretty much always you'll be dealing with short, int, and long. You hardly ever will need long for that reason. All right, so as I said, there's one bit for the sign of the number, and the rest is for representing the number itself. If you ever need negative numbers, if it never need negative numbers, always use unsigned. And it's signed by default. So if you don't say unsigned, it's a signed integer by default. And this is just a little way of shorthand writing. So I had short int and long int and long int. But for all the ones but int itself, you can actually omit the word int because short is guaranteed to be an integer anyway. So you don't need to actually say int there. It's just a little shorthand. All right. Any questions about integers so far? Okay. So if you want to, so sometimes if you need to put a literal on the right-hand side, but the literal on the right-hand side is too large to represent as an actual integer, then you need to put this capital L at the end. So what this means is, so let's say we have code like this. So if I have int x is equal to, so the largest number that a int can represent is approximately 4 billion because it has 32 bits, and 4 billion is approximately 2 to the power 32, which is the number of bits that we have available. So let's say that we wanted to try setting x to be 10 billion, which is definitely more than enough. So 10, that's 10,000, million, billion. So if we wanted to see out x, let's see what would happen. I actually don't know what. So it actually printed something completely different. So why do you think that is? It wrapped around, yeah. So here, this is, you can actually see there's a warning here. There's an implicit conversion from a long to an int. So the compiler already saw that this number is too large to represent as an int, but it's okay to represent it as a long. So if we change this to long, it should work, I think. But let's see. Yeah, it should work. But so this slide really isn't necessary for putting the L at the end, but it's actually a good idea to say this because it always communicates that you're explicitly saying the thing on the right is a long. Because in some situations, the literal on the right-hand side can be interpreted as an int, not a long. So if I put the L there, it explicitly says this thing actually is a long integer. And so then we get the value that we actually want there. Yeah. So so the way that what happens here is that since I said that the maximum that an integer can take is 4 billion, the way that this works is it actually is kind of hard to address without going into the hard details. But what happens here is that if we have some bit representation of this number, I don't know if this is actually the bit representation of this number, but it clearly needs more than 32 bits because it can't be stored in an integer, right? Because an int has 32, it's too large for an integer. So what happens here is that only the bottom 32 bits are taken here because I need to chop this down to 32 bits in order for it to work. And when it does that, it discards all of the other bits. And so it'll give me some 32-bit number, which happens to be the one that I showed earlier. So if I change this back, and then it prints this. This is the 32-bit version after it's called masking. So if I have this much larger number than 32 bits, take the bottom 32 and chop the others off, that's the number that happens to go there. But yeah, so that goes way more detail than I expect, but that's what I call wrapping around, although it's not the same as wrapping around.
So you're saying the ones that get chucked down and the ones that are used as binary for that number?
Yeah, I'm not saying that this, I don't even know what the binary of this number is. I'm just looking at some arbitrary binary number here. But I'm just saying that when it does this, this is what's called an implicit conversion, and we'll talk about that later. But what happens here is that the bottom 32 bits, I don't know if that's 32, but the bottom 32 bits are kept, and all of the other ones are thrown away, because I can't take more than 32 for the int here. But if I change this to long, then long here on my machine has 64 bits. And 10 billion apparently can be stored within 64 bits. And so I don't need to do any chopping. But if I had even a much larger number, let's see, maybe this will work. I actually don't know what will happen. Oh, it even gives me an error. So it's actually too large to even represent at all. So, so this number is too large to do, but this implicit conversion thing will happen if you have something that's too large to represent as an int, but you store it into an int. But we'll talk about when we do the conversion stuff. Other questions about that? So just put the L if you want to be explicit. I've never come across doing this, but if you ever do, just be explicit if you can. Okay. And then if you want a long, you put 2 L's. But sometimes instead of, so what happens is, if you want to actually store a binary number, and you have the actual binary number there, maybe you want to, I don't know, store an address in the computer, which is represented by a binary number. Or you want to represent a binary number, but don't want to do the actual conversion to a decimal number to store it. Sometimes, because the binary version of the number is way too long, or it's actually really long, you may want to work in some other base to make it much easier to work with. So one that's not very common, but some people actually use, is base 8. So base 8 is take the binary version of the number, the zeros and ones, and group it into groups of size 3. So let's do an example. Let's see. So let's do an example. So let's say we have this number. Let's see if it's the right size. Yeah, okay. So let's say we have this binary number and we want to put it into base 8. So what we do is we group it into groups of size 3 all the way through. And then what we do is we convert that to a some number between 0 and 7, because base 8 can represent numbers between 0 and 7. So let's chop this up into groups of size 3. You should start on the right side and then move your way over, but this number happens to have 12 binary digits in it, and so therefore it's okay. Okay, so what is 011 in converted to decimal? 6? 3, right? Because this is the ones place, and then this one is the twos place. So 1 plus 2 is 3. Good. So we write a 3. So this is in base 8. What about this one? Well, it has the ones digit there, as well as the fours digit. So it's 5. So 5 is next. This one should be clearly 0. That should not be an issue. And then I think we saw this one before, which is 5. So this number is 3505 in base 8. Okay? So this number that I happen to have here is 75 in base 8. What if I wanted to convert this back to binary? Well, what is 0 in terms of 3 binary digits? 0, 0, 0. That should be no issue. Oops. 0, 0, 0. What is 7 in terms of 3 binary digits? 1, 1, 1. Because it's in the 4's place is a 1, 2's place is a 1, 1's place is a 1, so 4 plus 2 plus 1 is 7. So I have 1, 1, 1 here. And then 5. What is that? That's 1, 0, 1, as we already saw before. So in fact, the binary version of this octal number, base 8, is this number. Whatever that is, I don't know what it is. Okay? So do we know how to convert from base 2 binary into octal base 8? Yeah. So yeah, there's not much of a reason that I use for octal. I know that it's used in security sometimes, where you need base 8 for some applications. It's not really widely used, as I was saying. But sometimes you need it. If you want to actually specify the number, you put a 0 on the front, an explicit 0. That means to the C++ compiler, this number is in base 8. So in fact, we can actually see what happens. So let's say we want to figure out what is the decimal version of this number. So I put that there. I put 075. That indicates to C++, this is a base 8 number. And then let's just see what happens. So it actually is 61 in decimal. So cout always works unless you specify it otherwise in decimal. It always prints in decimal. Okay. And then the other one that's much more widely used is a hexadecimal, which is base 16. So instead of grouping them into 3 chunks, we group them into size 4 chunks instead. So this is the octal one of the first number. So let's move this down here. And then now, because it's 12 digits here, I can break it up into groups of size 4 pretty easily. So I would group them up like this. And so now I got to figure out what is the hex value of this number. So note here that the number that could be represented here can go beyond 9. So the way that it works in hexadecimal is that you use letters for the remaining values. So the highest value that you could represent here is when it's all ones, which is, it happens to be 15. So for values 10 through 15, we represent them by A, B, C, D, E, and F. But I think we won't have a problem here. So what is the what is 0111 in decimal? It's 7. We've already seen this. So it's 7. And then what about this one? 4, because it's only in the ones place. And then this one is 5. So this is hex 745 in 745 in hexadecimal. But if I wanted to convert this one back, so let's say we wanted to look at this one. What is the decimal version of this? So I'm going to have 4 bits for 7, 4 bits for 5, 4 bits for A. So what is 7 in 4 bits? 0111, we've already seen. 5, we've already seen, is 0101. What about A? Well, it represents 10 because it's right after 9. So what is A? What is 10 in binary? 1010, because we have the 8 lit up and we have the 2 lit up as well. So we group these together, and so that's the binary version of that number. Any questions about hex? Yeah. Yeah, so note, because we're grouping them in chunks of size 4, if I have, let's say, all ones in that 4 sequence, then I need to represent that as some value. Well, if we're just going to be continuing using 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's not enough to represent all 16 possible values, right? Because I can have a 0 or 1 in each of the places, so I have 16 values. So I need to represent 0 through 15, so 0 through 9 gets me part of the way there. I can just put 0, 1, 2, 3 all the way up to 9. But for the remaining ones, I don't have any digits left. And I can't just put 2 digits there because that would be interpreted as 2 hex digits. So the way we get around this is saying, well, A is going to represent 10, B is going to represent 11, C is 12, D is 13, E is 14, and F is 15. If we wanted to work in base 32, then we would use more of the alphabet. Okay? But it's just, it doesn't actually mean anything except just what it represents in binary. Yeah. Yeah, so then you would use more of the other characters, like all the special characters, that sort of thing. Other questions? Yeah.
So what if you have a binary number that doesn't evenly split?
Good question. So if we have a binary number that doesn't evenly split, then what do? So let's say we have something like this, that it doesn't evenly split into groups of size 3. So let's say we want to convert this number to base 8, octal again. So you start from the right side and break off into groups of 3s until you get to where you can't do that anymore. Then you put zeros on the front. So here I had 1 0 left, so then I just put 2 more so that I have an even group size 3, although that's not really necessary. And then I work with these groups of 3. So you always start on the right. So you do the same thing when you're working in decimal. You start on the right side of the number and you work your way forward. When you're putting the commas to denote the separation into tens, digits, hundreds, then thousands, then millions, then billions, you put the comma there. You start from the right side and you work your way forward until the left side of the number. So you do the exact same thing already. Yeah.
Is there a way to identify binary numbers?
Yes. So it's not written on this slide, so I don't expect you to know it. But the way that you do it in C++, I don't know whether you need C++11 for this, but the way you do it is with B. So then if you wanted to do something like this, so if I wanted to do 101, what is this number in binary, 101? 5. Yeah, because the 2's is missing. If it was a 1 there, then it would be 7. So if I printed this out, we should expect 5, and we do. So that's the way that you can specify a specific binary number. But as I said, it's quite cumbersome if you have a long binary number versus just putting it into hexadecimal, which is 4 times shorter. So that's why people like writing hexadecimal instead of binary directly. Any questions on that, though? Yeah. Ooh. The question was, if we wanted to have the user enter a binary number and then you wanted to work with that binary number. I actually don't know the answer. I'll look it up in office hours and I'll post an announcement about it. Yeah. I know there's a way in Python to do it. I don't know about C++. Yeah. But
have the program check that, like, use the make to check if it's binary, if it's not, have to do it.
well, so good question. So if I have this number right here, 101, do I mean the binary number 101 or the decimal number 101? How do you know? Well, if I write it like this, but what if I just tell you, I speak verbally to you and I say I have the number 101, do I mean binary or decimal? Don't know, right? So it's ambiguous in that sense. So if you get an input from in fact, you don't even know what base it's in. It could be in base 3, 4, 5, you don't know. So I'm sure that there's a way that you can convert a string of binary digits into an actual binary number, but I don't know. Yeah.
Kind of getting ahead of how we use
Yeah, we're not covering regexes in this class, but yeah, but that doesn't tell you that you're in a specific base or no. Yeah.
if they enter 0 in the number
But that's input from the user. So that would be a string of characters. But if they entered that, you might know that. But what if it was in base 16? Because B is a valid character in hexadecimal, right? So this whole idea of what should you present the input, how should you present the prompt to the user versus what should you expect from the user? That's actually quite difficult because the same input can be interpreted in multiple ways, right? It could either be in binary or it could be in decimal. You don't know. So if you expect a binary number, that's why having a good human readable prompt is very important. But any other questions about this? Okay, let's get back into this. Okay, so we talked about integers for quite a while. So now you may wonder, well, how do I represent like 3.5 on the computer, right? So we know how to handle a lot of integers here. How do I handle those types of numbers? So those are what are called floating point numbers. So it says that it's designed to hold real numbers, but this is actually not true. So that's what the goal of them is, but it can't represent all real numbers. So for example, you can't actually store the value 0.1 in a computer precisely. So you can get close and you can get very, very close to representing exactly 0.1, but you can never precisely store that particular value. So what you try to do is you try to get an approximation for how close you can get to representing that number. So you can try to store numbers like this. Yeah, so you can also store them in scientific notation. So the way, there might be a slide about this. Yeah, there's a slide about it, never mind. So on the next slide, I'll show you how to do scientific notation. They're always signed. Because the range of them is so vast anyway, you don't really need more storage for the vast majority of applications, but they're always signed. There, of course, are different sizes here. So float and double are the main ones that you'll use. And as you might expect, double is double the size of float. So float comes from floating point. Double just means double the size. And long double, I'm not sure. I think it'll have the same situation as long int before, but I'll have to check. Yeah, float is at most the size of double and at most the size of long double. All right. So if you wanted to actually have a floating point number, so literally written in the code as a literal, you can just write the number as is with a decimal point. So no surprises there. But you can use scientific notation as well. And you can use capital or lowercase here. So if you wanted to represent, so this one is actually 10 times pi, because this says this is 3.14159 times 10 to the first power. So the e here is has the base of 10. So just like normal scientific notation. And here is 6.25 times 10 to the negative 5. So if you work with scientific notation, I would definitely use this if you're going to use this in your program. They're double by default because the vast majority of people use double, so it's by default. But if you wanted to make this into a float, maybe you can't use as much memory, but you have to use something other than an integer, then you would put an F here, either capital or lowercase, either way is fine. And same situation with long before. it can be used for long double here. Okay, so you may wonder, well, that's fine and good, but what if I wanted to do that same thing? So if I had like 3.14 on the right side, so what do you think would actually happen here? So I don't have float or double on the left side, I have int. Yeah. So you say it's going to round up to 4? Oh, you mean round down to 3. Okay, so it'll round down to 3. What if I put 3.64 there? What do you think would happen? It would round up. Anyone have another opinion? Yeah. It goes down. Any other opinion? Yeah.
I think it goes decimal after that.
What do you mean by decimal? Oh, it'll be, well, 0.64 right here is in decimal. It's not in base 8 or whatever. It is in decimal. Yeah. Exactly. So what happened here is it'll print 3. So it's the same situation as when we assign something too large into an int. It chopped off the high bits and kept the low 32 bits. Same type of idea here. If you have something that's not represented as an int and you assign it to an int, it takes everything that's not part of an integer and just throws it away. So the thing that's not part of an integer here is the 0.64 bit. So it'll take that part away and it'll keep the 3 on the as the value that x has. So the either round down or what is called truncation, either viewpoint is the same. So let's just see what happens here. So the fractional part is always truncated if you assign to an int. If you assign to a float or a double, it'll keep the same value. So it's only when you assign to an integer type thing that it chops off the fractional part here. And this is basically what we just saw. Okay, and so dealing with a floating point with integers at the same time, that's actually quite an important thing to work with. But we'll see that towards the end of these set of slides. But any questions on how this works? Yeah.
So why would you use it?
Great question. So why would I ever use an int for this reason? Because I can just use a float or a double because they already represent the integers that an int or a long will already represent. Why would I ever need an int or a long if I can just use double all the time? Anyone have an idea? Yeah. That's not necessarily true, but it's a good idea, but it's not necessarily true. Why else might I do that? So one reason is it's easier to read, and another reason is it's for stability purposes. So if you have this code that says you're going to input an integer, you can definitely expect you're going to get an integer. What if you instead use a double and ask the user to input something? Could they put something that's not an integer? Yeah, because you specified it was a double, and then you asked for them to put an integer, but they're evil and they put something that's not an integer. Then the program will continue because your code says you can put any number that you want, not just an integer. So it's for stability purposes and what you are expecting in your code. Are you expecting an integer or are you expecting any real number? That sort of thing. Any other questions about this? Okay, so the next major type that we'll be using instead of just integers is a character or a char. So you can think of this as a single character. So the way that you write this is you put it in single quotes with a single character inside. So, and then it says here it represents some integer, but let's just see what happens. So if I say char, which is the type of character, and let's call it C, the name of the variable is C. And then maybe let's put capital C in quotes here. So C here represents the character capital C. So if I C out this variable, then I should expect that we'll print the character C, and in fact we do. So no surprises there. But the way that it's handled on the back end is chars are essentially just integers. So again, it depends on the system that you're working with, but chars usually occupy 1 byte of memory. So what happens here is since it's 1 byte, it has 8 bits to work with. And so chars are you can work with chars just like integers are. So you can think of it as a very short version of a short or an int or something like that. So here I have that when I have this C here, in memory, what is stored in that memory location is the value, in this case, 67. Anyone know where that 67 comes from? Yeah. It's from ASCII, yeah. So there's this neat table that if you search ASCII, and actually autocompletes for me. If we look at this table, these are, this is what is called the ASCII table. And so these are the normal characters that we're going to work with in C++. What happens when you work with a char is that it looks up in this table and says, what is the decimal version of this number? And it stores that decimal version. But it prints, when it wants to print or work with that value, it just looks up, hey, what is the corresponding char? What is the character associated with this number? And you can see that all of the alphanumeric characters are here. They're stored by some integer. You don't need to memorize this table. It's not important. But the key here is that a char is usually 1 byte, and it stores some number on the back end. Just like how ints work with, just how pretty much anything that we work with in this class, it stores some integer on the back end. But it's easier to us because we have a single character to work with instead of dealing with 67. I don't want to say int letter equals 67 because someone reading the code will look at 67 and go, I don't know what that means. But if they see the character C there, then it's much easier for the programmer to actually understand what is going on. Okay, a character literal is just one character surrounded by quotation marks. Nothing interesting really there. And of course, as you saw, when I had quotes with the C in it, then when I printed it, it didn't put the actual quotes there, it just printed the actual character. So just keep that in mind. What if I wanted to print, single quote mark, then C, or whatever this variable has, and then another quote mark? What would I have to do? Yeah. Right. And then I would actually have to do this 3 times, in a sense. So here, what I can do is something like this. So remember, a char holds a single character, but an escaped character, even though it looks like 2 characters, really is 1 character because it's just escaping this 1 quotation mark. So if we just did this, then it actually prints that 1 quotation mark. And then, of course, if I did the same thing on the other side, then I'll get a single quote mark on both sides. Okay? Any questions on how that works? Okay, so hopefully nothing really that interesting here. I hardly ever use characters here, but what is much more common by pretty much every single programmer who's ever lived is a string. So strings is literally just a bunch of characters in the same memory locations, in consecutive memory locations. So if I wanted to store a string which is in double quotation marks instead of single quotation marks, then what happens if you want to store that in memory, it stores individual characters in memory. So it stores H in some memory location, then it stores the little e in the next memory location, then L, then L, then O. So what happens, well, I'm not storing the quotation marks themselves in memory. So how does the C++ compiler know, hey, this is the end of the string? Because there's no indicator to say this O is the last character. What happens is what is called a null terminator. So this \0 is another escaped character, which signifies to say, hey, this is the end of the string. But the cool thing is that if you want to actually print this string out, it won't print that null terminator. So you don't have to worry about that null terminator being printed out. So if we wanted to do something like this, oops, I don't need this. So let's say that we have, we want to declare a string instead, and let's call it S, and then we called it hello. What if we wanted to see out S? Then what would happen is you might expect it prints the characters, but without the quotation marks or the null terminator. So the entire purpose of the null terminator, great test question by the way, what the purpose of the null terminator is to say this is the end of the string, to help the compiler know this is where the string ends. Okay. Any questions on how strings work? A string is just a bunch of characters together. It's just anything that's between two double quotation marks. That's all it is. Yeah. So you mean you can put the null terminator in a string? I don't know. I think you can, but let's see. So if I put a null terminator there, let's see what happens. Okay, so it runs until the first null terminator. Sometimes you may want to put a null terminator inside the string. There's an interesting story about that, but it's kind of a long story. But sometimes you want to do that, but just note that if you want to print it out, it'll just run until it sees a null terminator and think, oh, the end of the string is here, so therefore I don't have to do anything else. Okay? Any other questions about string? One more slide, I promise, and then I'll let you go. So, as we already saw, character literals have a single quotation mark with one character on the inside, and a string has two double quotation marks. But keep in mind, if I put double quotation marks around a single character, that's not a character. That is a string, because it's between two quotation marks. Could I, in principle, have two double quotation marks with nothing in between them? Could I do that? Well, what is one way that I can test whether that's a good idea or not, or it actually works or not? Just run it. So let's see. So anytime that you're not sure whether something in C++ actually works, make a program to run it and then check whether you're actually right or not. So if I do something like this, and then I run, it prints nothing, which is what we'd expect because there's no character there. This is what is called the empty string. And there are valid uses of the empty string, but I'm not sure we'll get to them, but we'll see what happens. Any questions on the difference between characters and strings? Okay. And I will let you go, and I will see you on Friday. Pick up your quizzes, please, because I don't want to have to keep carrying them.